Welcome friends. Welcome to Teach Tigers. I am Verender Singh, your physics mentor. Now, as you know, we are going through the video series on current and electricity. And in this session, we are going to see mechanism of current flow. Right? We will see that what is the phenomena and how exactly current flows inside a conductor. And what are the parameters on which this current flow depends. Right? In our previous session, we have seen the definition of electric current as well as we have seen the mathematical expression of electric current and what is the relation between current and charge. If you haven't seen that video, go to our playlist and go to lecture number 1 on current electricity. Right? So let's start the discussion on mechanism of current flow. Now if we talk about mechanism of current flow, so before understanding the mechanism, we have to understand a term called current density, right? So whenever we talk about current density, it means current per unit area. Now in our previous session, we have seen, say, if we have a conductor like this, and if I cut a cross section like this, if I cut a cross section area like this, then through this cross section area, the amount of charge that passes in unit time, that is basically current, right? Now here we define current density. Current density is basically represented by J, right? And it means current per unit area. It means current per unit area. Which area? The cross-sectional area, right? It means the current per unit cross-section area. So if we consider this as my cross-section area, then current through this cross-section area is basically my current density. That means current per unit area is basically current density, right? Now, from this figure, we can see, say if there are some positive charge carriers which are flowing in this direction and there are some negative charge carriers which are flowing in this direction, then we define this current density J as current upon area, right? And which area? The cross-sectional area, right? Now, but there is a important point which we have to keep in mind while writing this current density. And that is, we have to consider the area which is normal to the charge flow, right? This area A is the area which is normal to the charge flow. Always remember, this area is the area which is perpendicular to charge flow, right? That means we have to consider the area which is perpendicular to what? The flow of charge. Right. Now, as we can see here, this area, how we draw area vector here, we have seen in our previous lectures that area vector is perpendicular to the surface and it is outwards. Right. So if I am observing it from here, so this will be my area vector. And I can see this is current. Now both the vectors are parallel. That means this current is normal to the surface. Normal to which surface? The cross-sectional surface. Right? So this is very important. We have to understand that this current density is defined in such a way that this is current upon area, and which area? The cross-section area which is perpendicular to flow of charge. Right? Now, then suddenly a thing comes to our mind. What will happen if this cross section is not perpendicular? In that case, what we have to do? In that case, we take the component of area which is perpendicular to the current flow or the flow of charge, right? Let's see. Say if we have something like this, if we have an area which is now not perpendicular, we can see the area vector is like this. This is my area vector which is at an angle theta with this current. Now in that case, what I will do is, I will take the perpendicular component. See, if I say this is my area A, this is the cross section area A, then what is this component? This component of area will be A cos theta. That means the component of area perpendicular to what? Flow of charge. That is A perpendicular, which is A cos theta here. So, if I have to define current density here, then current density J will be I by A perpendicular. And what is A perpendicular? That is I by A cos theta. Right? I by A cos theta. So, if I move this term A cos theta here, what I will get? I'll get I is equal to J into A cos theta. And my dear friends, this current density is a vector quantity. That is the key. This current density is a vector quantity. So, if we see JA cos theta, what it will become? It will become J dot A. It will become J dot A. That means J vector and A vector ka dot product is our current. I is equal to J dot A. And if we have to define in terms of like this, then we say J is nothing but I by A perpendicular. That means perpendicular component of area and perpendicular to what? Perpendicular to the flow of charge. So this is how we define current density. Right? So I hope now it must be clear to you what is current density and how we define it. Right? Now this is very important to understand that current density, this J is a vector quantity. Let me put a vector sign here. Then a question comes that what is the direction of this current density? So always remember, direction of this current density is same as the direction of current. The direction in which current is flowing, that is the direction of current density J, and magnitude wise it is I divided by A perpendicular. So now let's take up an illustration based on this thing, and it says a copper wire of length 1 meter and radius 1 mm is joined in series with an iron wire of length 2 meter and radius 3 mm. Say, let's picture it down. So this is my copper wire, and we are given that this copper wire is 1 meter. The length of this copper wire is 1 meter, and what is the radius of this wire? Radius we are given is 1 mm. Let it be 1. So R1 is 1 mm. Right? Now, after that, it is joined in series with a wire like this, and this wire is iron wire, right? And we are given that length of this iron wire is 2 meter, and radius of this wire, say let it be R2, is 3 mm. Right? Now, they are saying that a current is passed through the wire. The ratio of current densities in the copper and the iron wire is. So, like we have discussed in our previous lecture, that if a current I is passing through this wire, same current is going to enter into this wire. That means this cross section area is not at all going to change this current. Right? If current I is going through this wire, same current I will enter into this wire. Right? So now, if current is going to be same, then we know our current density is J is equal to I by A, and there is no need to take like that A perpendicular, right? Because here A, the area is perpendicular to the flow of charge, right? We can directly take it like this. So this J is I by A. Therefore, we can say that this current is same. So this implies J1A1 is equal to J2A2, right? Where J2 is what? J2 is current density in this second wire, A1 is the area, A2 is this area, and J1 is the current density, right? Because current is same, so therefore JA is constant. Therefore, we can say J1A1 is equal to J2A2. Now, we have to find the ratio of current densities. That means if we ratio of current densities in the copper and iron wire, so we have to find J1 upon J2. Now, what will be J1 upon J2? It will be simply A2 upon A1, right? and we know area of cross section will be pi r square. Therefore, we can say this is equal to pi r2 square by pi r1 square. From here, pi and pi will cancel out. We will get r2 square by r1 square. Now, what is r2? r2 is 3 mm and r1 is 1. Therefore, if we substitute the values, we will get 3 square by 1 square. What it will be? This implies the ratio of current densities J1 to J2 is 9:1. Right? This way we can easily calculate the ratio of current densities. Right? All we have to remember is, in such cases, current is always and always going to be the same. And if current is same, we can directly establish this relation that J1A1 is equal to J2A2. Right? So I hope now it must be clear to you how we handle current densities related to a current carrying conductor. Right? Now let's move forward. As we can see, it is 9:1. Our answer is right. So next topic that comes is a drift velocity. It is very important. We have to understand it. It is represented by letter Vd. Right? Now, to understand drift velocity, let us consider a conductor. So this is my conductor, and in this conductor, say electrons are there. Now we know in conductors, it is the free electrons which are responsible for current flow, right? Because positive charges are bound inside nucleus, it is only the free electrons which results in the flow of current, right? So there are free electrons available in this conductor, and these electrons are free to move, but there is no force available at this moment which is going to push them. So I am considering a normal state, like there is a conductor and it is in random state. There is no battery or anything attached to it. So under normal situation or under normal condition, what we say that these electrons, they are in random motion, right? Under normal motion, under normal condition, these electrons are in random motion. Random motion means they are moving like this on a random path, like this. This is how they keep on moving. So if we see their velocities will be like this. They are randomly oriented. There is no fixed direction of these velocities, right? They are randomly moving here and there. Now, as a result, if we calculate the overall velocity, of these electrons, it will come out to be 0, because they are randomly moving here and there and they are nullifying each other. So what we say, under normal condition or under normal situation, net current flow inside a conductor is always 0. Reason being, because these electrons, they are randomly moving here and there, and overall effectively they are not having any motion in a particular direction. They are having a random motion, and this random motion, they will cancel out each other, they will nullify each other, and as a result we get nothing. That means, as a conclusion, we can keep this thing in mind that in normal state or a normal condition, net current or net charge flow inside a conductor is always 0, and it is because of the random motion of electrons, right? So now what will happen if I say that how I can make current to flow inside a conductor? For that, I have to apply an external force which is going to orient these electrons in a particular direction. And how we can do it? We can do it by applying a potential. By applying a potential across a conductor, we can orient all these electrons to flow in one direction. Let's see. Say this is my conductor, and say if I connect this conductor to a battery. Here's the battery. Now what is the role of a battery? Role of battery is to apply a fixed potential across a conductor, right? So role of this battery is to apply a fixed potential across this conductor. Say this is A and this is terminal B, right? This is terminal A and this is terminal B. This is positive terminal of the battery and this is negative terminal of the battery. Now the role of this battery is to apply a fixed potential difference. That means between terminal A and B, there is a fixed potential difference. This terminal A will be at higher potential and this terminal B will be at lower potential. We will discuss all these things later on. Now, whenever there is potential difference, we know potential difference leads to what? Electric field. We have seen this in electrostatics. Wherever there is potential difference, there is electric field. And or in other sense, we can say in the direction of field, potential decreases. Therefore, electric field will be like this, from positive to negative. Then only we can say that in the direction of field, potential is decreasing, because this is at higher potential, this is at lower potential. Right? Now, this is my electric field. Right? From A to terminal P. Right? Now, this electric field is also present inside this conductor. This electric field is present inside this conductor. And inside this conductor, there are free electrons. Right? There are free electrons present like this. Now, what will happen to these electrons when an electric field is applied? We know a charged particle when placed in electric field always experiences a force. And we know positive charges experiences a force in the direction of field, whereas negative charges always experiences a force in the direction opposite to field. We have discussed all these things in detail in electrostatics. I guess it was in lecture number 4 or 5. Right? If you have some doubt regarding this thing, go back to our series of lectures on electrostatics and see like video 4 or 5 it may be. Right? Just go through those videos. Right? So, if there is a charged particle, negative charge or positive charge, whenever it is placed in electric field, it always experiences a force. Now here, the charged particles are electrons. Therefore, they will experience a force in the direction opposite to field. Right? So, let's draw the force vectors. They will experience a force like this, in this direction. And what is the amount of force or the magnitude of force? The magnitude of this force Fe is, we know, Q into E, where E is the external electric field. This is the amount of force which they will experience. Right? Now, next thing is, if a force is applied on these electrons, what will happen? For sure, these electrons will start moving. Right? For sure, they will start moving. The velocity with which they will start moving is called drift velocity. Right? The velocity with which these electrons start moving is called drift velocity. And it is represented by letter Vd. Right? And why they started moving? It is because of the force. And how this force is generated? Because of this electric field. And this electric field is generated because of this battery. That means ultimately it is what? Ultimately it is the battery which is going to give a flow of charge. Right? Or we can say that this battery is ultimately responsible for the flow of charge. Right? Now, next thing is, if a force is acting on these electrons, that means they should accelerate as well. But I am saying they'll move with a velocity Vd. So, is this velocity is going to be constant or is it going to increase with time? Because a force is acting on them. That means there must be an acceleration. So, that means this velocity is going to increase with time. But it does not happen here. These electrons, they actually move with a constant velocity. Then the question comes, how is it possible here? There is a force, there must be acceleration. If there is acceleration, how is it possible that they are moving with constant velocity? The question is correct. How is it possible? The thing is, you must have noticed, we have not defined simply velocity, we have defined drift velocity. Now, what is the meaning of this drift velocity? In actually, what happens is, inside this conductor, these are free electrons, and along with these free electrons, there are fixed atoms and ions as well. Now, when a force is applied on this electron, it will try to increase its velocity. But when it will try to increase the velocity, in between there are some fixed atoms and ions. Now these electrons will collide with those atoms and ions, and ultimately they will lose that velocity. Then again they'll start moving, and again they'll collide, and again they'll stop. Again they'll start moving, again they'll collide, and again they'll stop moving. So it is just like a drift. They are not actually moving free. They are not moving free flow. There is not a free flow movement. Rather, they are actually drifting from one place to other, then next, then next, then next. It is like a drift of electron. Therefore, this velocity is called drift velocity, right? And this is not a ever increasing velocity. Don't think it that way, that there is a force, because of this force this velocity is going to increase. No, it will not happen like this. These electrons, they rather drift in forward direction, right? So it is the drift velocity, and we assume this drift velocity to be constant over a period of time, right? So we assume this drift velocity to be constant over a period of time, because it is like it is 0, then increasing, then becoming 0, then increasing, then becoming 0. So on average we say that this is a constant velocity. This is how we assume this, right? So never think that this velocity is an ever increasing velocity, right? So I hope now it must be clear to you what is drift velocity, right? The velocity with which these electrons are getting drifted, that is called drift velocity. That is one thing. Second thing is, if these electrons are moving in this direction, that is from B to A, then what will the direction of current? For sure, the direction of current will be from A to B. We have discussed it in our last lecture. The direction of current is always opposite to the direction of flow of electrons, right? This is the second point. Then next term, a very important term that comes is called relaxation time, and it is represented by letter tau. Relaxation time. Now what is relaxation time? So relaxation time is basically the average time between two successive collisions, right? It is the average time between two successive collisions. Which collisions? The collisions of these electrons with the atoms and ions. So it is like, say, if an electron is initially at rest, it will start moving, it will start gaining some velocity, then it will collide. Again, it will slow down, it will again increase its velocity, again it will collide. So the average time between two successive collisions is this collision time or relaxation time. So what is relaxation time? Relaxation time is the average time between two successive collisions of electron with neighboring atoms and ions, right? So this is how we define relaxation time, right? Now we have understood this term relaxation time. We have understood what is drift velocity. Now let's move that relation between current and this drift velocity. Let's try to establish this relation between current and drift velocity. So let's see how we can do it. I'm again assuming the same thing, that there is a conductor like this, and there is a battery connected here like this. This is positive terminal of the battery, this is negative terminal. This terminal A will be at higher potential, there will be electric field like this, and because of this field, these electrons, they will experience a force like this. They will start moving in this direction. With which velocity? With drift velocity, and a current is established in this direction, right? This is how it happens. Now we will try to establish a relation between current and drift velocity. Now first of all, we know what is the force which is acting on one electron. It is E into E, right? Charge on one electron multiplied by the electric field, that is QE, we know, right? So because of this force, what is the acceleration which these electrons are going to gain? So the acceleration which they are going to gain is Fe upon mass of one electron. This m is the mass of one electron, right? So it will be E into E upon m. This is the acceleration. Now if we talk about this drift velocity Vd, then this drift velocity, or the average drift velocity rather we say, the average drift velocity will be, how we can find this average drift velocity? we can use the formula v is equal to u plus at. And we assume that initial velocity of these electrons is 0. That means the average drift velocity Vd will be equal to A into T. What is A? That is E into E by M multiplied by tau. Tau is the relaxation time, right? Because we are considering the motion when an electron started moving and when it collided with other atoms and ions. That much motion we are considering. So what we say, this drift velocity Vd is E tau by M. Now this is the expression for drift velocity, which is E tau by M. And you must remember this expression. This is very important, right? You'll need it at a number of places. What is drift velocity? It is E tau by M, right? Now, just do one thing, quickly note it down, and then we'll move to our next part, that is we'll derive a relation between current and this drift velocity. Quickly note it down. So, I hope you must have noted it down that drift velocity is E tau by M. This is a very important expression. You have to remember it, right? So now let's try to establish a relation between current and this drift velocity. Now, we know how we define current. We define current as charge per unit time, right? Charge per unit time. Now, what is this charge? This charge is number of electrons multiplied by electrons, because this Q is the total charge. And what is the total charge? Is the number of electrons multiplied by charge on one electron divided by the time, right? But whenever you go to market and you purchase a conductor, then they'll not specify the number of electrons that are going to be present inside the conductor. Rather, they'll specify the current density, the electron density, that is small n. Now, what is small n? Small n is number of electrons per unit volume. This is what they specify. Now, whenever you purchase a conductor from market, there is a rating, and ratings are always density, right? Density of the electrons. So what they specify, that the density of electrons in this conductor is this much. They don't specify you the exact number of electrons. That means we have to calculate the number of electrons using this. So if we consider this conductor, then say A is the cross section area, L is the length of the conductor, right? A is this cross section area, L is the length of the conductor. Then what will be the volume of this conductor? Volume of this conductor is area of base multiplied by height. That is how we define volume of a cylinder, area of base multiplied by its height. So volume of this conductor is going to be A into L, right? Now, we know small n is the number of electrons per unit volume. That means unit volume or a single volume, again I am using the unitary method, unit volume contains this much number of electrons, right? Then what will be the number of electrons in AL volume? It will be N into AL, because this much number of electrons are present in unit volume, and in AL volume, if we have to calculate the number of electrons in AL volume, what we will do? We will multiply this N with AL. So this will be the number of electrons. Let me substitute it here. This current I is equal to N AL into E by T, right? So this is what? This is NAL E by T. Now, one more thing. If we see in this conductor, how we can relate the flow of electrons with time. That means we are assuming that these electrons are drifted with a constant velocity. If they are getting drifted with a constant velocity through this conductor of length L, that means this velocity will be equal to what? Speed is equal to distance into time, L into T. Or what we can say is speed is equal to distance upon time. It will be like distance upon time, right? So how we define VD? VD as distance upon time. Which distance? The length of the conductor. That means these electrons, they are drifting with velocity VD through this length L in time t. This is how we relate. And because we are assuming that they are moving with a constant velocity, because this drift velocity, we are assuming it to be average velocity, right? Average constant velocity. Therefore, we can apply this formula, right? Speed is equal to distance upon time. Now, if we see in this expression, this L upon T, we can replace it with VD. So, expression which we will get is I is equal to NEA VD. Now, this is the expression which you have to remember. First expression which you have to remember is VD is equal to EE tau by M. That is one. Second expression which you have to remember is I is equal to NEA VD. We are going to use it at a number of places. This is very important, right? You must remember this expression. I is equal to NEA VD, right? So, let's move forward with the note that you remember the formula of current and its relation with the drift velocity. It is I is equal to NEA VD, and you know the expression for drift velocity, that is EE tau by M, right? Let's move forward. Let's take up an illustration. It says a conducting wire of cross-section area 1 centimeter square. Say we have a wire with cross-section area of 1 centimeter square. Now it is very important, whenever you start any illustration or whenever you start any question, always picture it. That is the most important thing. In physics, like if you are able to draw the correct picture, then there is a high probability that you will get a very correct and the right answer, right? So always try to picture it now. So we have a conductor whose cross section area is 1 centimeter square. It has 3 into 10 raised to the power 23 per meter cube charge. Now what is this? It is very important to understand this thing. Units dhyan se dekhiye. This is what? This is the electron density. That means they are saying this much number of electrons are present in 1 meter cube of volume. That means this is what? This is electron density. That means 3 into 10 raised to the power 23 electrons per unit volume. That means this is small n. Right? Then if wire carries a current of 24 milliampere, now we are given current which is 24 milliampere, that means 24 into 10 raised to the power minus 3 ampere. The drift speed of the carrier is, we have to calculate the drift speed. Like we know current I is equal to NEA VD. In such questions, it is very important to be careful about the units, because more or less in such questions, these are direct formula based questions. How they play with the units, right? The conversion of units we have to be very careful, right? So I is equal to NEA VD. What is current? It is 24 into 10 raised to the power minus 3. This is equal to N, which is 3 into 10 raised to the power 23. Then charge on electron. Then area. Area is 1 centimeter square. Again, you have to convert it to meter square, right? If you will convert it to meter square, it will be like 10 raised to the power minus 4 into VD. So, you can directly write VD and you will solve this equation. Here is VD. You can directly solve it. Simple calculations are there. And the answer which we'll get is 5 into 10 raised to the power minus 3. This is the drift velocity, right? So just formula based application, you can do it easily, right? And based on this topic, you will get questions like this only. There will be directly formula based. Only thing is which you have to keep in mind, you have to very careful about is the unit conversion. Like the area is centimeter square, you have to convert it to meter square. That is important thing. Similarly, like you have to be careful about they are given the density in meter cube. Sometimes what they do is they give density in centimeter cube. There you have to convert the centimeter cube to meter cube, right? So that is the only variation they can do. The rest is just the formula, right? Now, this is end of concepts, guys. So it is all about drift velocity, its relation with current, and at the end, I need that you should remember these two formulas. I really, we are going to use this formula in our coming lectures, and these two formulas which are current and drift velocity formula. The current and drift velocity relation is I is equal to NEA VD and drift velocity which is EE tau by M. You have to remember these two formulas. They're very important, right? Later on in our application part, we are going to use them at a number of places. So just keep a note of all this, all the concepts which I have discussed, and then we'll start with the application part, right?